In this lesson, we want to talk about angles in trigonometry. All right, so let's start out the lesson by talking about some basic definitions. We'll think about the concept of a line segment, and a ray. So let's suppose that we have two distinct points, and here on the screen you'll see that you have a point A and also a point B. So those two distinct points can be used to determine a line. Okay, so you see we've drawn a line through them. We can also use those letters, the A and the B, to name the line if we want. So we could call this line AB like this, or we could also put the AB and we could put a line on top like this. Now, I want you to notice that you have arrows at each end, okay, and that tells you that the line continues indefinitely in each direction. Now, similarly, you have something known as a line segment. With a line segment, it's just a piece of a line or a part of a line. So notice how you have an endpoint here with A and an endpoint here with B. So here it doesn't continue indefinitely in each direction. It's a finite or countable length from the point A to the point B. So this is your line segment AB, okay? And you can also write it like this. You can put AB with a little line on top, and you're not going to have arrows there. It's another line segment that's put on top of AB. Okay. Lastly, we're going to talk about the concept of a ray. So here you have one endpoint, okay, in this case it's going to be A, and it's going to extend through this point B indefinitely, okay? So we see this arrow here, it tells us that it starts at A and continues through B indefinitely. So this is going to be the ray AB, or you could write AB, and you can do this. All right, so now I want to talk about an angle. And basically an angle consists of two different rays with the same endpoint. So when we talk about the two rays, these are the sides of the angle, and the common endpoint is the vertex of the angle. So if we look at our example here, we have a ray AC. So we have a ray AC. And then we have another ray, which is AB. So another ray, which is AB. So these are going to be the sides for my angle, okay? Additionally, A is the common endpoint, so that's my vertex. Now, if I'm naming the angle, then I can call it angle CAB. You can go in order like that. Or you could go the other way. You could say angle BAC, okay? Or you could just use the letter of the vertex. Now, we can write out angle each time, or you can use this special symbol. So you can use this symbol here, and I could say, okay, this is angle CAB, or it's angle BAC. Okay, notice how A, the vertex, is in the middle each time. And then also I can just use the letter of the vertex. So I can say this is angle A. All right, now associated with every angle is going to be its measure, which is generated by a rotation about the vertex. So the measure will be determined by rotating a ray starting at one side of the angle, which is called the initial side. So let me just highlight that. For in this case, the initial side is here. We'll talk more about the standard position later on in the course. For right now, our initial side is going to be right there, okay? So that's the starting position, and then we rotate to the other position on the other side, which is known as the terminal side, which in this case is right here. So you can imagine that you started with two rays that are on top of each other. So this guy represents this guy in the end, and I know I'm not drawing that perfectly well, but basically you can think about starting here and then just rotating about the vertex to get here. So this is your initial side where the two are on top of each other, and then it rotates to the terminal side where you still have one ray here, or one side, and then another ray up here. Now, when we rotate in a counterclockwise direction, so meaning I start here and I rotate this way, okay, that's how I'm measuring. Well, what happens is I generate a positive angle. Okay, now if I go the other way, if I go clockwise, I'm going to generate a negative angle. We'll talk more about this as we progress through the course, but basically if I started this way and I went that way, okay, now I'm generating a negative angle. Now you could imagine if I started here and I went this way around to generate the same terminal side, okay, well now I would have a positive angle because I'm going counterclockwise for the rotation. Okay, so we'll talk more about this as we progress. All right. So when working with angles, we're often going to measure our angle using the degree. Okay, so this is a unit of measure for us. We'll also see radians here shortly. But for now, when we work with the degree, we assign 360 degrees to one complete rotation of a ray. So in other words, what we're saying here is that the terminal side of the angle will correspond exactly to the initial side when it makes this complete rotation. So you can see this image that we have here, and you can imagine that we started out with two rays that were on top of each other, okay? And then we rotated it completely around. So it's one complete rotation here. And we assign the value to that angle 360 degrees. Okay, so that's one complete rotation. Now, of course, you're going to have a lot of scenarios where you make more than one complete rotation or less than one complete rotation. So if, for example, you made 1 over 360, that amount of a complete rotation, well, we would just take this number in the numerator here, which is 1, and we would say that we have 1 degree in this case, okay? We can also write this using our degree symbol, so we can say it's 1 degree like that. If you had, for example, 5 over 360, okay, that amount of a complete rotation, this would be now 5 degrees, okay, that would be the measure of that angle, and you can, of course, still write it like this, 5 degrees. Now, when we work with angles, we're going to have some terminology that we have to get used to. So the first guy I want to talk about is an acute angle. Okay, so this is where the measure of the angle is greater than 0 degrees, but less than 90 degrees. So you see you have this Greek letter here, theta, and in trigonometry, we often use these Greek letters to represent an unknown angle. So here, this is just some unknown angle. Again, theta here, we'll say that theta is greater than 0 degrees, but less than 90 degrees. So this is an acute angle. Now, we've all seen right angles in our algebra course, especially when you're talking about the Pythagorean formula. But a right angle, in case you don't know, you're going to denote this with this special symbol here, okay? And this is where your angle is exactly 90 degrees. Okay, so theta here we can say is exactly 90 degrees. So next we want to talk about something known as an obtuse angle. So this is an angle that is greater than 90 degrees, but less than 180 degrees. So here we can say that theta is greater than 90 degrees, okay, the right angle, but strictly less than 180 degrees, which we'll find out in a minute is a straight angle. So for the straight angle, what we're going to have is theta is going to be 180 degrees. And basically what you have here, you can imagine you start out with, again, two rays on top of each other. You make half of a complete rotation. Okay, so this guy ends up right here, okay? And you end up with what looks like a straight line, right? But basically you started with two rays on top of each other, you made half of a complete rotation, and now the two rays are facing away from each other, okay? And in terms of the complete rotation, we know the degree measure is 360 degrees. This is half of a complete rotation, so half of 360 is 180, so that's why theta here is 180 degrees for your straight angle. All right, so let's wrap up the lesson and talk about complementary and supplementary angles. So we'll start with complementary angles, and basically when the sum of the measures of two positive angles is 90 degrees, the angles are known as complementary angles. So here's a typical example. You can see that the bigger angle here, if I started from here and I rotated here, this is a 90-degree angle. Again, this is given to us by this symbol right here, okay? But we have these two smaller angles, and we want to find out their measure. So you have one that's given by this guy right here, 15x plus 12 degrees, and another that's given by this guy right here, the 12x minus 3 degrees. So to find the measure of each angle here, we use the fact that, again, the complementary angles sum to 90 degrees. So I'm going to take this measure here, which is 15x plus 12. I'm going to leave the degrees off for now. Then plus this measure here, which is 12x minus 3. I'm going to set this sum equal to 90 for 90 degrees. So we're going to solve this, and basically 15x plus 12x is 27x. Then 12 minus 3 would be 9, and this equals 90. So what I'm going to do now is just subtract 9 away from each side of the equation. And of course, this is going to cancel. We get 27x is equal to 81. Divide both sides by 27, and you're going to get that x is equal to 3. So let me write that up here. We'll say that x is equal to 3. So we're not done. We need to find the measure of each angle here. And x equals 3 just tells you what you need to plug in. Okay, so don't stop there. So we would have 15 times this 3 plus 12. Okay, so 15 times 3 is 45. 45 plus 12 is 57. So the measure here that you're looking for is 57 degrees. Okay. Then the other guy is going to be 12x minus 3. So 12 times 3 and then minus 3. 12 times 3 is 36. 36 minus 3 is 33. So the measure of this angle here is 33 degrees. And you can see that the measure of 57 degrees plus the measure of 33 degrees gives you a measure of 90 degrees, which again is the measure of the bigger angle. Okay, so now let's talk about supplementary angles. So we already know that a straight angle here, so if I started here and I rotated, again, this is a half of a rotation. This forms a straight angle. It's 180 degrees, okay? Half of 360 degrees, 180 degrees. That's how you remember your straight angle. So when the sum of the measures of two positive angles is 180 degrees, the angles are known as supplementary angles. So this example is basically the same in terms of how you set things up. You have this angle here that's 9x minus 5 degrees, so 9x minus 5. You have this angle over here, which is 5x plus 3 degrees. So I just put those two as a sum. So 9x minus 5 plus 5x plus 3. So I've got my sum going there. And I set it equal to 180 for 180 degrees. Again, that is the full angle, right? If I consider this all the way from here to here, it's 180 degrees. And so what we do here is we just solve. 9x plus 5x is going to be 14x. Negative 5 plus 3 is, of course, negative 2. So this equals 180. Let's go ahead and add 2 to both sides of the equation. We get 14x is equal to 182. We can divide both sides by 14 and find that x is equal to 13. So x is 13. Again, don't just put that and stop. You need to plug in to find out your measures, okay? So 9 times 13 minus 5. 9 times 13 is 117, minus 5 is 112. So this guy is 112 degrees, okay? And then 5 times 13 is 65. Let me write that out. So 5 times 13 is 65, plus 3 is going to be 68, okay? So this would be 68 degrees. So again, if you look at the sum of 68 degrees and 112 degrees, you get your 180 degrees, which once again is the total measure of this angle, right? So if we think about the whole angle, including this smaller angle and the other smaller angle, is 180 degrees. So we would expect that 68 degrees plus 112 degrees to sum to 180 degrees, and in fact, it does. In this lesson, we want to talk about angle measures in degrees, minutes, and seconds. All right. In our last lesson, we talked about some of the basics that are involved with angles. And we also learned about the unit of measure known as the degree. It's how we can measure our angles. We also have radians, but we'll talk about that later on. So we learned that a complete rotation, or one complete rotation, is assigned the value of 360 degrees in terms of the measure of the angle that is produced. So let's say I started with two rays that were on top of each other. Again, I take this ray and I rotate it completely around, okay, completely around. So what happens is the measure of that angle is assigned a value of 360 degrees. Now, if I think about this in terms of 1 over 360, so let's say I made that amount of a complete rotation, well, this is now going to be 1 degree. If I made 5 over 360, that amount of a complete rotation, that's 5 degrees, so on and so forth. Now, what happens when we need to measure an angle where the amount of the rotation is less than a degree? So it's a portion of a degree, a part of a degree, a fractional amount of a degree. Well, what we're going to turn to here is going to be minutes and seconds. So this is pretty easy to work with. Basically, you start with the fact that if you have 1 degree and you divide it by 60, this produces a unit known as the minute. Okay, so this is going to give you 1 minute. So this is your notation for the minute. Okay. Now you could also say that 60 minutes is going to give you 1 degree, right? So these two statements are saying the same thing. I can take 1 degree and divide it by 60 and get 1 minute. Or if I multiplied both sides by 60, okay, and cleared the denominator, well, what I'd have is 60 minutes equals 1 degree. Okay, so that's the same thing there. Now, also, we can go smaller. Okay, so we can take our minute, so 1 minute, and we can now divide this by 60, and we're going to get a unit of measure known as the second. Okay, so we're going to say 1 second like this. So that's going to be your notation for that. Okay, and we can also, again, just multiply both sides by 60, and we can say that 1 minute is equal to 60 seconds. Okay, so pretty easy to remember overall. Now, additionally, you can start with 1 second, okay, and you can say this is equal to, again, 1 minute over 60. And this would be equal to what in terms of degrees? It would be 1 degree divided by, now you'd have 60 times 60, which is 3,600, okay? So we'll use this later on. This is something you probably want to write down in terms of these formulas so that you're going to be good to go when you're doing your homework. All right, let's go ahead and look at the first problem. We're just going to add two of these guys together. It's very simple. You just need to understand how the carrying process works. So let me explain. I'm just going to set this up vertically. You don't have to, but I think it's easier to do it that way. So let's just set this up vertically. So 19 degrees, we got 50, and we got 17 here. So what I have here is 37 degrees, 15 minutes, 45 seconds, plus 19 degrees, 50 minutes, 17 seconds. Okay, so we're adding this together. So we know when we do a vertical addition, since we have a base 10 system, if you get a digit that is 10 or larger, you do a carrying process. Well, here, because of the way we convert things, we're looking for a value of 60 or larger to carry. So when I add 45 plus 17, I get 62, right? So basically, this is saying that I have 62 seconds. But again, if we go back up here, we know that 60 seconds equals 1 minute. So really what I could say is that this is 1 minute and 2 seconds, right? So this is the carrying process you're going to use. You're going to put 2 seconds down here, and you're going to carry this 1 into the next column, okay? Just like if you were doing a vertical addition, it's no different. It's just you're changing the way you think about things because you're using 60 now, okay? So in this one, I've got 1 plus 15 plus 50. So 1 plus 15 is 16, 16 plus 50 is 66. So again, now we have 66 minutes, and again, if we go back, we know that 60 minutes equals 1 degree. So I can say that this is 1 degree and 6 minutes, okay? So I'm going to put my 6 minutes down here. I'm going to carry my 1 degree up and over to the next column. And now I'm good to go. I do 1 plus 37, which is 38, and 38 plus 19, which is going to give me 57, so 57 degrees. So the answer here would be 57 degrees, 6 minutes, and 2 seconds. All right, now let's move on and talk about a subtraction problem. So you're going to find the process very similar to vertical subtraction. So let's just go ahead and set this up. So we have 14 here, degrees, 18 minutes, 30 seconds. We have 9 degrees, 25 minutes, 50 seconds. So put my subtraction sign out here. And what you're going to do is think about the fact that, again, I have 30, I have 50. So I want to subtract here. So what I have to do is borrow, right? And think about the fact that 1 minute is equal to 60 seconds, right? So if I take 1 away from this and make this 17 minutes now, I can take this and convert it into seconds. So I can say 30 seconds plus 60 seconds would be 90 seconds. So I'm just going to put 90 seconds there. I'm just borrowing. Again, just like I do with vertical subtraction, same thing. I've just got to get used to that number of 60, okay? So 90 minus 50 is going to be 40. So this is 40 seconds. Then when I get over to this column here, I've got to do the same thing again. So I've got to borrow. I'm going to borrow here and put this as a 13 degrees. And remember, if I think about 1 degree, it's equal to 60, okay, 60 minutes. So I'm going to add 60 to 17. That's going to give me 77, so 77 minutes. And then 77 minutes minus 25 minutes is going to give me 52 minutes. So now I move into my leftmost column. I have 13 degrees minus 9 degrees. That's just going to be 4 degrees. So my answer here will just be 4 degrees, 52 minutes, and 40 seconds. Okay, let's find the complement and also let's find the supplement of the angle that's given. So we know that complementary angles sum to 90 degrees. We know that supplementary angles sum to 180 degrees. So if you're asked to find the complement of this angle, what I would do is I would subtract 90, okay, minus this 29 degrees, 15 minutes, 6 seconds. So of course you need to borrow here, so you can just go ahead and write this as 89 degrees, okay? And I'll put this as 60 minutes. You need to borrow again, so let's just write this as 59 minutes. And let's just go ahead and write this as 60 seconds. So all I did was I took the 90 and I borrowed again so we can do our subtraction, okay? So we go through now, we're good to go. 60 minus 6 is 54. So this is 54 seconds. 59 minus 15 is 44. So this is 44 minutes. And then 89 minus 29 is going to be 60. So this is 60 degrees. So the complement of this angle here is going to be 60 degrees, 44 minutes, 54 seconds. Now, similarly, you can erase this part. And up here, what I'm going to do is I'm going to put 179. Nothing else will change. Because if I put 180 there, again, I'd have to borrow and then borrow again. Okay, so this is how you would set it up. And once you've done this, it's very easy. You just go through and say, okay, well, 60 minus 6, we know that's 54, so 54 seconds. 59 minus 15, again, we know that's 44, so 44 minutes. And then 179 minus 29 is 150, so 150 degrees there. So the supplement of this angle would be 150 degrees, 44 minutes, 54 seconds. All right, so now what we want to do is go from this decimal form here, this 114.09 degrees, to degrees, minutes, and seconds. So this is a pretty common task and very easy to do. So in the end, you want something that looks like this. You're going to have degrees, you're going to have minutes, and you're going to have seconds, okay? So you take the part in front of the decimal point, the 114, that whole number part, and just put it right here for your degree. Okay, so it's 114 degrees. You're good to go with that. Now, you move on to the part after the decimal point. So this 0.09. So 0.09 degrees is what I have left over after I fill that out. Now you want to convert this into minutes first, okay? So remember, 1 degree is equal to 60 minutes. So to get this in terms of minutes, I need to multiply by 60, okay? So I would take this, and let me just erase this. We don't need this. So times 60. This would give me 5.4, okay? 5.4. Now, this now is in terms of minutes. So this is in terms of minutes. I'm going to take the whole number part again, and I'm going to just drag that up here. So I'm going to put 5 here, and now I'm going to say that I have 0.4 minutes. So remember, when you think about it, you have 1 minute is equal to 60 seconds, okay? So I'm just going to multiply this now, this 0.4, by 60 to get it in terms of seconds, and this is going to give me a value of 24, okay? So when we convert this over, what we end up with is 114.09 degrees is 114 degrees, 5 minutes, 24 seconds. And if you have a TI-83 or a TI-84, it will actually do this conversion for you. You want to type this number out first. Then you want to key up your angle button, which is usually second and then angle. And you want to go down to the DMS for degrees, minutes, and seconds. When you hit that, it's going to give you this out as an output. Okay, so that's another way to do it if you want to use your calculator. All right, so to wrap up the lesson, we want to look at this 119 degrees, 5 minutes, and 15 seconds. And we want to put this into a decimal form. So how can we do this? Well, we're going to start with this 119 here, and then put a decimal point. And we want to think about the 5 minutes, how can we convert that? And the 15 seconds, how can we convert that? Well, I want you to remember that, again, when we think about it, 1 degree is equal to 60, okay, 60 minutes. But also we said that 1 degree divided by 60 was equal to 1 minute, okay? So if I have 5 minutes, okay, if I have 5 minutes, just think about the fact that that would be 5 degrees divided by 60. Okay, so I would say that I could divide this by 60, okay, and I can get this in terms of degrees. Well, 5 divided by 60 is going to be 1 over 12, but I'm going to reduce this in a minute because I'll talk about this further. You're going to end up with this nasty repeating decimal. So just leave this alone for right now. All right, so to get this part in terms of degrees, remember I told you in the beginning that basically if you had 1 second, okay, it was equal to 1 minute divided by 60, okay? And 1 minute divided by 60, we could say is 1 degree divided by 3600, okay? So to get this in terms of degrees, we need to divide by 3600. So let's erase this. So let's erase this and divide by 3600. Okay, so at this point, you would really be adding these two amounts together, and basically from those amounts, you would get a decimal that you can put on here. Now, in a lot of cases, you're going to get a nasty repeating decimal for each of them. It doesn't happen all the time. Sometimes it works out nicely. But my suggestion to kind of limit that is to just get a common denominator going. So I'm just going to multiply this by 60 over 60. This is going to be 300 plus 15 over 3600. And this is going to be 315 over 3600, okay? And this is going to work out to a nice decimal for us, which is 0.0875. So 0.0875, and this is in terms of degrees. So not bad overall, just a lot of things to remember in terms of what the conversion is. Okay, once you kind of have that memorized, it's very, very easy to do. And a lot of times nowadays, you can just do this on your calculator. In this lesson, we want to talk about angles in standard position. And also we want to talk about coterminal angles. All right, so an angle is in what we call standard position if its vertex is at the origin and its initial side lies on the positive x-axis. So that's all it is. That's the whole definition. So in this example here, you see we have a little 35-degree angle. And we can see that our vertex is at the origin, okay? And we can see our initial side is on the positive x-axis. So this guy is in standard position. Now, additionally, when we have an angle that's in what we call standard position, it's said to lie in the quadrant where the terminal side lies. So in this case, my terminal side lies in quadrant 1, okay? So this guy would lie in quadrant 1. Now, additionally, you remember that these guys go counterclockwise. So this is quadrant 2, okay? So if you had an obtuse angle, you'd be in quadrant 2. If you had an angle that was greater than 180 degrees but less than 270 degrees, you'd be in quadrant 3. And then if you had one that was greater than 270 degrees and less than 360 degrees, you'd be in quadrant 4, okay? Now, something to keep in mind, you might get an angle whose measure is some multiple of 90 degrees. So it could be 90 degrees, 180 degrees, 270 degrees, 360 degrees, so on and so forth. Well, in this case, we have something known as a quadrantal angle, okay? So you will not be in any quadrant, okay? So that might be a question for you on your test. So another little quick example of this, we have another angle that's going to be in standard position. So again, the vertex is at the origin. The initial side is on the positive x-axis. This guy is a 160-degree angle. So it's an obtuse angle, and it's going to lie in quadrant 2, right? Because that's where its terminal side is. Okay, so let's talk a little bit about getting an angle measure that's larger than 360 degrees. We already know that the complete rotation, or one complete rotation of a ray, represents an angle whose measure is 360 degrees. So we've seen this in pretty much every video at this point. So we have two rays on top of each other. If I rotate this guy completely around, so one complete rotation, that angle measures 360 degrees. And let me put 360 degrees there. And basically, if we keep going, we can generate angle measures that are greater than 360 degrees. So as an example here, you can see that we have a 450-degree angle. So a 450-degree angle. And we generate this by making one complete rotation. So one complete rotation, so to right there, okay, where the terminal side would be on top of the initial side. And then we keep going another 90 degrees. So you'll notice how this looks like a right angle or a 90-degree angle, but basically we show here that we made one full rotation plus we went another 90 degrees. So to get this 450 degrees, we take the 360-degree angle, again from one complete rotation, and we add to that 90 degrees. We know from here to here is 90 degrees because this is a right angle. And so we add those two amounts together and we get 450 degrees. Okay, so that's where this guy comes from. All right, so now let's talk about these coterminal angles. So the concept here is that coterminal angles are going to be angles that have the same initial side and also the same terminal side, but differ by amounts of rotation. So the measures are going to be different by some multiple of 360. Okay, and I'll show you how to calculate that in a moment. But basically, if we look at this first example, you see that you have a 55-degree angle and you have a 415-degree angle. So the same initial side, the same terminal side. To get this first 55-degree angle, we start here and we just rotate here. That's all we do. But to get the 415-degree angle, again, you're going to make more than one complete rotation. So you're going to go around once. Okay, so that's 360 degrees. And then plus another 55 degrees. So in other words, you took 360 plus your 55. Okay, let me put my degree symbol in each case. And this gives us the 415 degrees that we see from that angle. Now, to show this without making a little diagram or a little graph, what you could do is just subtract. Okay, so you can either do 415 degrees minus 55 degrees, and that would give you 360 degrees. Or you could go the other way. Okay, it's going to be negative, but it doesn't matter. You're looking for some multiple of 360 degrees. Okay, so if you did 55 degrees minus 415 degrees, you would get negative 360 degrees. Now, let's look at another example of this. In this case, you have one positive angle and one negative angle. So this works as well. You have the same initial side and the same terminal side. So this guy is a negative 45-degree angle, and this guy is a 315-degree angle. So we start here and we go, again, if you're going clockwise, it's a negative angle. So this is a negative 45 degrees. The other one, we're going counterclockwise, so it's positive, and we go in this direction, so we're going around, and this becomes 315 degrees, okay? If you were to subtract the 315 minus a negative 45, so 315 degrees minus a negative 45 degrees, remember, minus a negative is plus a positive, you would get 360 degrees. If you were to subtract negative 45 degrees minus 315 degrees, you would get negative 360 degrees. So again, the way that you subtract is not going to matter. Okay, you're just looking for some multiple of 360 degrees to determine if these guys are coterminal. Again, same initial side, same terminal side. They're going to differ by some multiple of 360 degrees. That's all it is. Let's look at the first example. So we have 110 degrees and 470 degrees. A lot of you can eyeball that and see that the difference between those two would either be, if you did 470 degrees minus 110 degrees, obviously that would be positive 360 degrees. And if you did 110 degrees minus 470 degrees, that would be negative 360 degrees. But again, you're just looking for some multiple of 360 degrees. It could be positive, it could be negative, doesn't matter. Some multiple of 360 degrees. So in this case, we know these guys are coterminal. Okay, for the next one, we have 135 degrees and we have negative 495 degrees. So again, you can just subtract. You could do 135 degrees minus a negative 495 degrees, which would be 135 degrees plus 495 degrees. In this case, that would give you 630 degrees, okay? And if you don't know off the top of your head if that's going to be a multiple of 360 degrees, you just divide by 360 and see if you get a remainder. So if I punch that up on my calculator, I get 1.75. So to say you don't have a remainder, remember, you want something that's either a whole number or an integer, right? You don't want a decimal part or a fraction or something like that, right? You want a whole number or an integer. So because we have 1.75, we know that 630 is not divisible by 360. So this guy is not some multiple of 360. So these guys are not coterminal angles. All right, for the next one, we have 335 degrees and 2,135 degrees. So again, you can just subtract. You can subtract in any order. If I do 2,135 degrees minus 335 degrees, that's going to give me 1,800 degrees, okay? And if I took 1,800 and divided by 360, I would get 5. So we can say that their measures differ by some multiple of 360, okay? So they are going to be coterminal angles. Okay, let's look at another example that you'll see in this section. So they'll tell you to find the coterminal angle that is between 0 degrees and 360 degrees. So for this guy, there's kind of a slow way and a fast way. The slow way is to just keep subtracting or adding, depending on the situation you're given, 360 degrees until you get into the desired range. So I could subtract off 360 degrees and then do it again, and I'd be in the desired range. I can kind of eyeball that and say, okay, well, if I subtract it, take some nice round number. Let's say we take 400. So I take 400 twice. Okay, that's 800. I know if I subtracted 1,020 minus 800, I'd have 220. So I know I'd be about where I need to be. So what I'm going to do is I'm going to take 360 and multiply it by 2. That gives me 720. So this is the amount I want to subtract away from here. Again, it's the same thing as if I subtracted away 360 and then I subtracted away 360 again. Okay, that's all I'm doing. So I'm going to subtract away 1,020 degrees minus 720 degrees. This is going to give me exactly 300 degrees, okay? And we are in the range that we wanted between 0 degrees and 360 degrees. Okay, the last example is negative 596 degrees. Again, if you want to find a coterminal angle where it's between 0 degrees and 360 degrees, in this case, you need to add, because it's a negative, 360 degrees until you get where you need to be. Okay, so I know if I add once, it's not going to be enough. Again, I can just use 400 and say, okay, negative 596 plus 400, just approximating, is going to give me negative 196. So I know I'm not in the range with that, so I'd have to add again. So if I added again, I'd be at 204, okay? And that seems like that's where I want to go. Okay, so what I want to do is say, okay, I need 2 times 360, which again is 720, okay? So I'm going to take negative 596 degrees and add 720 degrees. Of course, what you're going to do there is just subtract, right? So you would do 720 degrees minus 596 degrees, which would give me 124 degrees. right? So in this case, I'd have 124 degrees as my answer. This would be the coterminal angle with this guy, okay? That fits the criteria where it's greater than 0 degrees and less than 360 degrees. In this lesson, we want to talk about angle relationships and similar triangles. All right, for the first example, we're going to look at a problem that involves vertical angles. This is something very simple. Basically, vertical angles are angles opposite of each other where the two lines cross. So you can see here we have these two lines that cross, and at this intersection point, you have angles 1 and 3 that are across from each other. Okay, so those are vertical angles. And then you also have angles 4 and 2 that are across from each other. So those are vertical angles, right? You can show it like this with matching arcs. So I can just do 2 like this here and 2 like this here. And what I'll do is I'll do 1 here and 1 here, okay? So angles 1 and 3 would have the same measure, and angles 4 and 2 will have the same measure, okay? That's a property of vertical angles, just saying that vertical angles are going to have equal measures. If we want to find the measure of angles 1 through 4, what we do is we say, okay, we're given the measure of angle 1, it's 10x plus 35 degrees. We're given the measure of angle 3, it's 20x minus 55 degrees. Okay, well, what we can do is set angle 1, which is again 10x plus 35 degrees, equal to angle 3, which is 20x minus 55 degrees. That's going to give me the value for x, and then I can plug that back in and find out what is angle 1, what is angle 3. So I'm going to go ahead and just subtract, and let me scroll down and get some room. I'll come back up to the diagram in a minute. So I'm going to subtract 20x away from each side of the equation, and let's go ahead and get rid of this. And I'm going to subtract 35 away from each side of the equation. So let's go ahead and get rid of this. And then if I do 10x, okay, 10x minus 20x, that's going to give me negative 10x. And this is equal to negative 55 minus 35 is going to be negative 90. If we just divide both sides by negative 10, we're going to find that x is equal to 9. Okay, so let's erase everything. And if you're on a test or something like this, you just have to plug into one of these because, again, these are vertical angles, so the measure is the same. Okay, so we know that x is 9. And if I plug in, 10 times 9 is 90. 90 plus 35 is going to be 125. Okay, so the measure of angle 1 is 125 degrees. Okay, 125 degrees. And also the measure of angle 3 is 125 degrees as well. Okay, and you could plug in there. And again, if you plugged in a 9, 20 times 9 is 180. 180 minus 55 is 125. Okay, so that's where you get the 125 degrees. Now, the other thing that you would note here is that these guys' angles 1 and 2 are going to be supplementary angles, right? Their measure is going to add up to 180 degrees. If you kind of rotate this, you can see that this guy right here, again, this is a straight line. Okay, this is a straight line. So if I took the measure of angles 1 and 2, let me just do this as a full arc here, okay? This would be 180 degrees, right? It would be a straight angle. So we know that the measure of angle 2 can be found by taking 180, okay, degrees and subtracting away 125 degrees, and that would give us 55 degrees, okay? And again, because angles 2 and 4 are vertical angles, I can just put this as 55 degrees as well. Okay, so our answer for this problem is that we have 125 degrees for the measure of angles 1 and 3, and then 55 degrees for the measure of angles 2 and 4. All right, so let's look at an example that involves a transversal that intersects parallel lines. So we see that 8 angles are formed here. You have 1, 2, 3, 4, 5, 6, 7, 8. Okay, those angles there have certain properties. So the ones I want to draw your attention to, we have interior angles. So you can think about this as being between the parallel lines, or some people say inside of the parallel lines. So those would be the angles 3, 4, 5, and 6. Okay. When we have alternate interior angles, they're going to have equal measure. Okay. So angles 3 and 6, those would have equal measure. And then also, let me kind of change this up. Also, angles 4 and 5 would have equal measures. Okay, so if we look at the alternate exterior angles, so the exterior angles would be, you can think about this as outside of the parallel line, so angles 1 and 2, and then 7 and 8. The alternate exterior angles will have equal measures. Okay, so we can say that would be angles 1 and 8, and then also we can say angles 2 and 7. Okay, so we can use these properties to find out the value for all 8 angles here. So if we start out with the fact that angle 2 has this measure, 11x minus 53 degrees, and angle 8 has this measure, 4x plus 8 degrees, well, let's think about the fact that angles 2 and 7 are alternate exterior angles, right? Alternate exterior angles, so they would have the same measure, okay? So I can really write that the measure of angle 7 is 11x minus 53, okay, degrees. Okay, so we know that angles 7 and 8 together form a straight angle, right? Or an angle that's 180 degrees. So in other words, angles 7 and 8 are supplementary angles. So what I can do here, I can add 11x minus 53 plus 4x plus 8 and set this equal to 180, again for 180 degrees. I can solve for x, I can go back and plug in and find out what is the measurement of each angle 1 through 8, okay? So what I'm going to do here, 11x plus 4x is going to be 15x, and then negative 53 plus 8 is going to give me negative 45, so minus 45, this equals 180. Okay, so if I add 45 to each side of the equation, let me scroll down and get some room going, then what am I going to have? This is going to cancel, and if I do 180 plus 45, I'm going to get 225, and this over here is still 15x. If I divide both sides by 15, I'm going to get that x is equal to 15, okay? So let's erase this, and we're just going to plug in. You can get rid of this, okay? We're going to plug in a 15 starting here. So what is 11 times 15? That's going to be 165. And if I subtract away 53, I get 112. So I know that the measure of this guy is 112 degrees. Again, alternate exterior angles, okay? Alternate exterior angles have the same measure. Okay, so this guy, 2 and 7, have the same measure. So this is 112 degrees here. Remember that vertical angles have the same measure. So that means that 7 and 6 have the same measure. Okay, so this is 112 degrees. 2 and 3 have the same measure, so this is 112 degrees. Okay, so at this point, you know 4 of your angles. And again, you can figure out the rest. You can plug in here if you want. You can plug the 15 in and do it that way. Or you can just take 180 and subtract away 112 and get 68 and fill out the rest, right? Because again, if I plugged in a 15 there, 4 times 15 is 60. 60 plus 8 is 68, so this is 68 degrees. Or again, you can use the fact that 7 and 8 are supplementary angles, so you can subtract 180 minus 112 to get the 68 as well. Now again, 8 and 1 are alternate exterior angles, so they have the same measure. And then again, you can also say that 1 and 4 are vertical angles, so they have the same measure. And 8 and 5 are vertical angles, so they have the same measure. Okay, and there's lots of different ways to go about getting these values, but you can see that for angles 1, 4, 5, and 8, the measure of the angle is 68 degrees. And then for angles 2, 3, 6, and 7, the measure is going to be 112 degrees. All right, so let's look at some examples now that involve triangles. So what you need to know here is that the sum of the measures of the angles for any triangle is going to be 180 degrees. So with this example here, we're given angles 1, 2, and 3. And the measure of angle 1 is 6x plus 1 degrees. The measure of angle 2 is 10x minus 56 degrees. And the measure of angle 3 is given, it's 43 degrees. So all we really need to do is set these guys as a sum, and it will be equal to 180 degrees, okay? So if we set up a sum here, so we'd say 6x plus 1 plus 10x minus 56, then plus 43, and this will be equal to, let me drag this down because I'm going to run out of room here. And let me just get some room going. So this will be equal to 180, okay? And we just solve for x, very simple. So 6x plus 10x is 16x. 1 minus 56 is going to be negative 55. Then negative 55 plus 43 is going to be negative 12. So I'll put minus 12 here. This equals 180. If we add 12 to both sides of the equation, we're going to get that 16x is equal to 192. You get some room going here. To finish things off, I'm going to divide both sides by 16 and get that x is equal to 12. So x is 12 here. So let me erase all this. So we said that x was 12. So for angle 1, if I plug in a 12 there, 6 times 12 is 72. 72 plus 1 is 73. So the measure of angle 1 is 73 degrees. Okay, and you can put it here as well. This is 73 degrees. For the measure of angle 2, it's going to be 10 times 12, which is 120, minus 56, which is going to be 64. Okay, so this will be 64 degrees. And I'll write that in here. This is 64 degrees. We're already given the fact that this is 43 degrees. And again, if you sum these amounts, you're going to get 180 degrees. All right, for the next two problems, we're going to see typical examples where we're dealing with similar triangles. So hopefully you remember this from geometry, but essentially if you have similar triangles, then corresponding angles must have the same measure, okay? Then secondly, corresponding sides must be proportional. So that means the ratios of their corresponding sides must be equal, okay? So for the first problem, we're going to deal with the statement that says that corresponding angles must have the same measure. Okay, so we have these two similar triangles, and I'm just going to call this first one triangle ABC. So I'll say triangle ABC is similar to triangle DEF. Now, what you want to do is match up the corresponding angles for this problem. You'll notice that the corresponding angles have matching arcs. Okay, so we have one arc here and one arc here. So angle A corresponds to angle D. And then you have two arcs here and two arcs here. So angle B corresponds to angle E. And then you have three arcs here and three arcs here. So angle C corresponds to angle F. Now, as we just said, corresponding angles, if you have similar triangles, they must have the same measure. So what that tells me is that if I know the measure of angle F is 144 degrees, then I also know the measure of angle C is going to be 144 degrees as well. If I know that the measure of angle A is 18 degrees, that tells me that the measure of angle D is 18 degrees as well. Now, what I don't know here is the measure of angle B and the measure of angle E. So let me fill out this guy right here. I'll just put E and I'll put a question mark. And for this one, I'll put B and put a question mark. Now, how can we figure this out? Well, remember, when we think about the sum of the measures of the angles of any triangle, it's going to be 180 degrees. So what I could do is take 180 degrees and subtract away the sum. So in each case, it's 18 degrees plus 144 degrees. So this sum represents the angle measures for two angles, and 180 degrees would be the sum of all three. So if I take this one, subtract away the sum of the two, I'm going to get the missing one. So let's put this as equal to, so 18 degrees plus 144 degrees, that would be 162 degrees. So this, let me just slide this down, would be 180 degrees minus 162 degrees, which gives me 18 degrees. So if we're trying to find the measure of angle B, it would be 18 degrees. And again, because angle B corresponds to angle E, they're going to have the same measure. So this is 18 degrees as well. So if you wanted to know the angle measure for all of these guys, well, in this bottom triangle, the measure of angle A is 18 degrees. The measure of angle B is 18 degrees as well. And the measure of angle C is 144 degrees. And then in the top triangle, the measure of angle D is 18 degrees. The measure of angle E is 18 degrees. And the measure of angle F is 144 degrees. All right, for the last problem here, let's look at an example with similar triangles where we're asked to find some missing side lengths. So this is a very easy problem to solve. It just deals with proportions. And essentially what you're going to do here is look at these two guys, and generally you're going to be given a statement that says something like triangle ABC is similar to triangle DEF. Now, we already know about finding the corresponding angles. You could do it based on the way that I read the two triangles. So again, I said triangle ABC is similar to triangle DEF. So that tells me that A is going to correspond to D, B is going to correspond to E, and C is going to correspond to F. Or again, you can use those matching arcs. So you have a single arc here and a single arc here. So B and E are going to correspond. You have a triple arc here and a triple arc here. So A and D are going to correspond. And then a double arc here and a double arc here. So C and F are going to correspond. Now, when it comes to side lengths, a lot of times you just have to write things down if you're given a not so easy scenario. Here it's very easy, you can match things up, but sometimes the triangles are flipped all the way around and stuff like that, so it's not so easy. So you might want to write the statement out and say triangle ABC is similar to triangle, in this case, DEF. And then you can just match things up. So I can say this side AB is going to correspond to this side DE. So here's my side AB, here's my side DE, those are corresponding sides. Then I have the side BC that's going to correspond to the side EF. So here's my side BC and my side EF. You can see those are corresponding sides. And then lastly, you can say this side AC is going to correspond to this side DF. So here's my side AC, my side DF. Those are corresponding sides. Now we know if we're working with similar triangles that corresponding angles must be equal, and corresponding sides must be proportional. So again, this just means that the ratios of their corresponding sides must be equal. So let's use that to set up a little proportion. So I know that this side AB corresponds to this side DE. Okay, so what I'm going to do is write the ratio of the length of this side AB to the length of this side DE. So I'm going to set that up as a fraction. I'll just say this is AB, so that's going to denote the length of this side. 2, this will be DE, so that'll be the length of this side. I'm going to say that's equal to the ratio of, let's go ahead and say, the length of the side BC, so the length of the side BC, to the length of the side EF. So the length of the side EF. So let me write that in there. And again, we know that BC and EF are corresponding sides. And I'll also say this is equal to the ratio of the length of the side AC, so that's going to be right here, so AC, to the length of the side DF. So DF is going to be right there. So once you have this set up, I would go through and plug in what you can, and then you're just going to solve for what you don't have, okay? Now, before I even do that, a lot of people are going to ask, why did I choose to put the AB on top and the DE on the bottom here? And it actually doesn't matter. You could flip this, but you have to stay consistent. In this case, I wrote the information from the smaller triangle over the information from the bigger triangle, but I could have also set this up as DE over AB is equal to EF over BC is equal to DF over AC. Okay, so as long as you stay consistent, you're going to be good to go. So I'm just going to keep it like this, and I'm just going to replace what I can. So for the length of this side AB, it's 15. So I'm just going to replace this with 15. For the length of the side DE, it's 30. So I'm going to replace that with 30. Now, 15 over 30 is 1/2. So let's just simplify that and say it's a half. Now, for the length of the side BC, it's 30.5. So let me put that in. And then for the length of the side EF, that's an unknown, right? So we don't know the length of that side. And then for the length of the side AC, that's 24. So this is 24. And for the length of the side DF, that is unknown. Let's grab this real quick. And I'm just going to solve one of these at a time. So I'm going to pick the one on the left and say 1/2 is equal to 30.5. This is over. Again, the EF is the length of the side EF. So cross multiply, and you would get EF is equal to 2 times 30.5 is 61. So the length of the side EF is 61. So you can come back up here and just put that this is 61 right here. Or if you wanted to notate this, you could say EF. This just stands for the length of the side EF. That's going to be 61. Okay, let me put DF here, and we'll come back down. So I'm going to set 24 over DF equal to 1/2. You wouldn't want to set this equal here because you're not going to be able to solve. So I'm going to cross multiply again. So this is DF is equal to 2 times 24 is 48. So the length of that side DF is going to be 48. So coming back up, you can put 48 here and 48 here. In this lesson, we want to talk about the trigonometric functions. All right, so to define our 6 trigonometric functions, we're going to start with an angle in standard position. And we're going to name this guy using the Greek letter theta. So you have your angle theta there. Remember, in standard position, your vertex is at the origin. Your initial side lies on the positive x-axis, so this is your initial side. And then this guy over here is called your terminal side. So what we're going to do from here is we're just going to pick some point, okay, that's not the origin, that lies on the terminal side. So this point that I've chosen here, could be any, but I've chosen this one. This is going to be the point which is -6, so -6, Now for the formulas, you want something generic. So what I've done is I've just labeled this as point P with the coordinates x, y. Of course, you can fill that in with whatever you have. Here we have -6 for x and +6 for y. Now additionally, what we need to do to get started is we need to know about something called r, okay? So r is just going to take the place of d in the distance formula. So you remember that the distance formula, the distance between 2 points in the coordinate plane, is equal to the square root of, you have your x sub 2 minus x sub 1 quantity squared, plus you have your y sub 2 minus y sub 1 quantity squared, okay? So look at what we've done here. We have this point, again, generically, x, y are the coordinates. And we have this guy right here, which is the origin. Most books will call this the point O, okay, for origin. I'm just going to call it the point L because I don't want you to get confused with the coordinates there, 0 and 0, okay? It looks too similar. So point L here, 0, 0 is my origin. I also have another point here to form a right triangle, okay, which is point Q, which has the coordinates x, right, because it's got the same x location, and then 0, right, because it's on the x axis, so x, 0. So we can see that we can form a right triangle, and obviously you could use the Pythagorean formula to find the distance from point P to point L, or the origin, or you could just plug into the distance formula, which is much easier. Now what we're going to do is we're going to replace the D with an R, okay, and I'll explain why that occurs in a future lesson. Let's get to the unit circle first. I want to just keep this simple. Additionally, since we're working with a point that is 0, 0, I can replace this with a 0 and this with a 0, okay? And now I no longer have an x sub 1 and an x sub 2, or a y sub 1 and a y sub 2, so I can just drop this notation, okay? We know that x minus 0 is x and y minus 0 is y, so I can just really say this is x squared, okay, plus y squared under this radical, okay? So we've made that quite simple now in terms of the definition for R. All right, so let's take a look at the 6 trigonometric functions that we're going to work with. Remember, this R here that you see in these formulas refers to what I just wrote. It's the square root of x squared plus y squared. Now, as we move forward in the course, we'll see different ways to remember this. I know a lot of you think about the SOHCAHTOA, okay, if you've taken trigonometry before. But for right now, we're just going to keep this really, really simple. We'll get to that later on. So the sine of theta is going to be equal to y over r. Then the cosine of theta is going to be equal to x over r. Then the tangent of theta is going to be equal to y over x, where x is not equal to 0. The cosecant of theta is going to be equal to r over y, where again, y is not equal to 0. The secant of theta is going to be equal to r over x, where x is not equal to 0. And the cotangent of theta is going to be equal to x over y, where y is not equal to 0. All right, so let's go ahead and look at an example. Let's say that we're given the point 9, -9. And basically, it's going to be the terminal side of the angle theta in standard position is going to pass through this point. Again, 9, -9 would be the coordinates. And we want to find the values of the 6 trig functions here. So let's do a quick sketch. A lot of people like to do that to see what's going on. It's not completely necessary because you're just going to be plugging some things in, but just to get an idea of what's going on. So if we highlight this point here, again, this is 9, -9. That's going to be our point. Let's just call it P, okay? And basically what we're looking at is our angle here, theta, okay? So we want to find the 6 trigonometric functions based on this guy. So let's go back up and let's remember that this is our x value. So our x value is going to be 9. Our y value is going to be -9. Just pull it straight from this ordered pair here, okay? So this is your x and this is your y, okay? Make sure you bring the signs along for the ride. Then your r value is what? Remember, this is found by taking the square root of x squared plus y squared. So the square root of x squared, x is 9, 9 squared is 81, plus y squared. Y is -9, -9 squared is also 81. So you could really write this as 2 times 81 to make it a little bit cleaner, okay? Because you know that 81 is a perfect square. The square root of 81 is 9. So you could really say this is 9 times the square root of 2. To find all the trigonometric functions, you're just going to plug in what you're given, okay? That's all it is. So we go back up, and there will be easier ways to remember this. But for right now, we're just going to reference this. So sine of theta is y over r. So sine of theta is y, okay, which is -9, over r, which is 9 times the square root of 2. Okay, well, we know we want to rationalize this denominator. First off, we can simplify this because this would be -1, but we want to rationalize this. So let's multiply the numerator and denominator by the square root of 2. And this would give us what? It would give a negative square root of 2 over 2. Okay, so that would be your sine of theta. So let's erase this and just kind of make this a little bit cleaner. Okay, so we'll bring this down and bring this a little bit over. And so now let's look at the cosine of theta. So this is x over r. So the cosine of theta, okay, so this is x over r, x is 9, and again, r is 9 times square root of 2. And basically, you're going to get the same thing as this. When you rationalize, it would just be positive, okay? So you would cancel this with this and get a 1 here, and you'd multiply the numerator and denominator by the square root of 2. And essentially, you would have what? You'd have the square root of 2 over 2. So this is the square root of 2. over 2. Okay, so the next one is the tangent of theta. Okay, so y over x. So the tangent of theta. Okay, so what is y? That's -9. What is x? That's +9. So that would be -1. All right, so next we have these guys that we can find by just flipping things. Okay, so we know that the cosecant of theta can be found by flipping the sine of theta. Okay, because this is r over y, this is y over r. So all I want to do for the cosecant of theta is just flip this guy. Okay, so I would have 2 over the negative square root of 2. And if you're smart, before you rationalize that guy, you'll go ahead and flip it, right? Because now we have to rationalize again. So I'm going to multiply this by the square root of 2 over the square root of 2. And that would give me what? You have a negative out in front. 2 times the square root of 2 over this would be 2. And you can cancel. This would cancel with this. And you're just left with the negative square root of 2. Okay, so the negative square root of 2. So then we go back and we see that the secant of theta is r over x. So I'm just flipping the cosine of theta. And again, the only thing that was different between this one and this one is the sine. So I know that the secant of theta, okay, the secant of theta is going to be equal to the square root of 2. Again, you can go through this on your own. You would flip this, and let's just do it real quick so that nobody's confused. It's 2 over the square root of 2, and you multiply this by the square root of 2 over the square root of 2. And so what do you get? You get a 2 down here, okay? That's going to now cancel with this 2 up here. You're left with just the square root of 2, okay? So that's how we got that. Now, the last one is the cotangent of theta, and that is found by flipping the tangent of theta, okay? In this case, the tangent of theta was -1. So if you think about it, you really say that's -1 over 1. Flip it, you still have 1 over -1, which is still -1. So my cotangent of theta will be -1 as well. All right, so let's look at another example. We're going to change things up just a little bit. So you might also be asked to find the trigonometric function values of an angle when we know the equation of the line that coincides with the terminal ray. So I want you to think for a second. We all know that the equation of a line in standard form that passes through the origin looks like this. So it's something ax plus by equals 0. So for example, this x minus y equals 0, if I didn't consider this restriction, that would be a line that passes through the origin, okay? But what we're going to do here is we're going to restrict the x values to either be x is less than or equal to 0, or x is greater than or equal to 0, okay? And what we're going to get is a ray with an endpoint at the origin. Okay, so let's look at an example of this down here, okay? And what you see is that we have x minus y is equal to 0, okay? That line would be drawn if I extended it past this point. Let me kind of highlight this in a different color. If I extended it past this point, 0, 0. But we're going to restrict the x values to be greater than or equal to 0, so we're only going this way. So this is the endpoint, and we go this way. So this is your terminal side, okay? So you might see this as well. All you need to do is pick a point that's not the origin. So in this case, I've picked the point 3, 3, okay? And one way you can do that, if you haven't drawn this guy, you can just pick an x value that lies in this range. Again, don't pick 0. So let's say you chose 3. Plug in a 3 for x. So you know that x is 3. Solve for the unknown y. What's it going to be? In this case, you can eyeball it and see it's going to be 3 as well. But again, if you had to solve, you would just say, okay, 3 minus y equals 0. Let me go ahead and add y to both sides of the equation, and this would cancel, and I get 3 is equal to y. Okay, so x is 3, y is 3. And this is going to make it really easy for us to crank out those 6 trigonometric functions. So what I'm going to do here is go through them more quickly. So let's just write them out. So we have sine of theta, and this is equal to our y value over our r value, and we'll get r in a minute. Then we have our cosine of theta, okay? So this guy is going to be the x over the r, okay? Then you have your, let me slide this down a little bit, so it went a little too far over. So we have the tangent of theta. This is going to be equal to your y over your x. Now we can crank this one out right now because x is 3 and y is 3. Let me label this. This is x, this is y. So 3 over 3 we know would be 1. So let's just put that down right now. Okay, then we know that the cosecant of theta, okay, the cosecant of theta is found by just flipping this guy. So it's going to be r over y. Then the secant of theta, okay, the secant of theta is found by flipping this guy. So it's r over x. And then the cotangent of theta is found by flipping this guy. In this case, you flip 1, right? If you had 1 over 1 and you flipped it, you still have 1 over 1. So it's just 1. So what is r in this case? Well, you would have, let's scroll down and get some room going. So r is equal to the square root of x squared plus y squared. Okay, so x is 3, y is 3. 3 squared is 9. So you'd have 9 plus 9 or 18, right? So 18 is 9 times 2. 9 is a perfect square. It's 3 times 3. So pull that out and you'd say this is 3 times the square root of 2. Okay, so what I'll do is everywhere there's an r, I'll just replace it with 3 times square root of 2. So 3 times square root of 2 and 3 times square root of 2. And you can do it here as well. But what's going to happen is we're going to crank these out really quickly because these are going to be the same and these are going to be the same. Okay, because we have the same x and y value. So x and y, as I just said, are the same. So I'm going to put a 3 here and a 3 here. And you can put a 3 here and a 3 here. Okay. And very quickly, we can see that this cancels and this cancels. So this is going to be the square root of 2 in each case, okay? And we can write that more cleanly, square root of 2. And let's write that more cleanly, square root of 2. And in this case, we need to rationalize, right? So we'd have 1 over the square root of 2. And if I multiply by the square root of 2 over the square root of 2, well, down here I would have 2, okay? And up here I would have the square root of 2. So let's write this as the square root of 2 over 2. And this is the same, right? So this is the square root of 2 over 2. All right, so these were more simple examples. As we progress, we'll see things that are much more challenging. In this lesson, we want to talk about reciprocal identities, signs of trigonometric function values, and also how to find missing function values when we're given one value in the quadrant of the angle. All right, so let's begin our lesson by talking about the reciprocal identities. So in the last section, we talked about the 6 trigonometric functions. We found that some of these functions are reciprocals of each other. So keep in mind when we use the value of r, okay, r by definition is equal to the square root of x squared plus y squared. Okay, and we talked about that in the last video. So we see that sine of theta is equal to y divided by r, okay? And then cosecant of theta is equal to r divided by y, and then in this case, y is not equal to 0. We don't have to have that restriction for r there because r is always going to be a positive number, okay? But we do need it here because y could be 0. So these guys, the sine of theta and the cosecant of theta are reciprocals. So if you know one, you automatically know the other by just flipping the fraction, okay? Then the same thing goes when we look at cosine of theta, which is x over r, and secant of theta, which is r over x. Again, x is not equal to 0 here. Then again, when we look at the tangent of theta, which is y over x is not 0, and the cotangent of theta, which is x over y is not equal to 0, those guys are reciprocals of each other as well. So in your book, when you're talking about the reciprocal identities, let me erase this real quick, they'll write them in a specific way. So we can say that the sine of theta, okay, is equal to 1 over the cosecant of theta, okay? Then you could also say the cosecant of theta is equal to 1 over the sine of theta. Remember, if you have 1 divided by something, okay, all you're doing is you're ending up taking the reciprocal. So if I had 1 divided by y over r, you could really say this is 1 over 1 times the reciprocal of this guy, so r over y. So this ends up being r over y. Okay, so that's all that is. It's just fancy notation. So let's erase this real quick and let's keep going. So we have the sine of theta is 1 over the cosecant of theta. The cosecant of theta is 1 over the sine of theta. Then you say the cosine of theta is equal to 1 over the secant of theta. Okay, and then the secant of theta, again, it's just 1 over the cosine of theta. Let's write these down here. So the tangent of theta is equal to 1 over the cotangent of theta. And of course, lastly, the cotangent of theta is going to be equal to 1 over the tangent of theta. Okay, so that's all this is. It's not very complicated when you see this in your book, the topic of reciprocal identities. You take the two guys that are reciprocals, okay? One will be over here, one will be in the denominator. You can switch the positions again. The sine of theta and the cosecant of theta, those guys are reciprocals. So the sine of theta is equal to 1 over the cosecant of theta. Similarly, the cosecant of theta is equal to 1 over the sine of theta. And you see the same thing with the cosine of theta and the secant of theta, and with the tangent of theta and the cotangent of theta. So let's look at a quick example of this. So we have that the secant of theta is equal to 9/2 or 9/2. What is the cosine of theta? Well, again, the secant of theta and the cosine of theta, those guys are reciprocals of each other. So if this guy is 9/2, all I have to do is flip it and it would give me 2/9. All right, let's take a look at another example. So here we have the sine of theta is equal to the negative of the square root of 6/3. What's the cosecant of theta? Again, these guys are reciprocals. So I can just flip them and say this is 3 over the negative square root of 6, okay? And what I'm going to do is I'm just going to put my negative out in front, and then I'm going to multiply the numerator and denominator by the square root of 6, so I can rationalize the denominator. So this will be equal to the negative of, we'll have square root of 6 times square root of 6 is going to be 6, and you'll have 3 times square root of 6 up here in the numerator. Of course, you can cancel. This would cancel with this. Each is divisible by 3. So this would just be 1, so you can just get rid of it. And 6 divided by 3 is 2. So your final answer here would be the negative of the square root of 6/2. All right, let's talk about the signs of the trigonometric function values. So we know that when we defined the trigonometric functions, we gave r as the distance from the origin, or the point 0, 0 to the point x, y. So since this distance is going to be undirected, okay, the value of r is always going to be positive. So if you look at something like sine of theta, okay, we know that this is defined as y over r, okay? So since r is always positive, we think about the sign coming from just whether or not y is positive or negative. So if you look at your coordinate plane, remember there's 4 quadrants. In the first quadrant, you have the x and y values that are positive. In the second quadrant, the x values are negative, the y values are positive. In the third quadrant, both the x and y values are negative. And in the fourth quadrant, the x value is positive, the y value is negative. Okay, so where is y negative? It's negative in quadrants 3 and 4. So that means if I'm in quadrant 3 or 4, the sine of theta is going to be negative because r is always positive, right? You would end up with a negative over a positive, which gives me a negative. Okay, and I should have put a negative there. But if you look at this little table I have up here, this summarizes everything for you. In the first quadrant, where x and y values are positive, all your 6 trigonometric functions are positive. In the second quadrant, where x is less than 0 and y is greater than 0, your sine of theta is going to be positive, and then the reciprocal, the cosecant of theta is going to be positive as well. As we move into the third quadrant, where again x and y values are both negative, you get just that tangent of theta and cotangent of theta. Again, those guys are reciprocals. Those guys are positive, everything else is negative. And then in the fourth quadrant, where x values are positive and y values are negative, you'll see the cosine of theta and also the secant of theta. Again, those guys are reciprocals. Those guys are positive, everything else is negative. So an easy way to remember this, because trying to remember this chart is kind of hard, is a little mnemonic device. All students take calculus. Okay, so just take the first letter from each. So all A, students S, take T and C for calculus. So all students take calculus, and this goes counterclockwise. So this is for quadrant 1, this is for quadrant 2, this is for quadrant 3, and this is for quadrant 4. Okay, so the A just stands for all, so all 6 trigonometric functions in quadrant 1 are going to be positive. The S is for sine, okay? So the sine of theta, okay, is going to be positive, and you know the reciprocal of that will be positive as well. The reciprocal of the sine of theta is going to be the cosecant of theta. So sine of theta and cosecant of theta are positive in quadrant 2. Then in quadrant 3, you have T for tangent of theta, and then also the reciprocal, the cotangent of theta, so those guys are positive, everything else is negative. And then in quadrant 4, you have a C for cosine of theta, and the reciprocal of that is the secant of theta. So again, those two are positive, everything else is negative. All right, so let's use what we just learned to look at a few examples. We're going to identify the quadrant of the angle based on these conditions. So we have that the cosine of theta is greater than 0 and the cosecant of theta is less than 0. Let's turn to our all students take calculus once again. Quadrant 1, quadrant 2, quadrant 3, and quadrant 4. The way I look at it is I just say, okay, well, cosine of theta is greater than 0. So where does that occur? It occurs in quadrant 1 and also quadrant 4. Remember, the C is for the cosine of theta, and it tells you that the cosine of theta and the secant of theta are going to be positive, everything else is negative. So let me just write below this that it's quadrant 1 and quadrant 4 that satisfy that condition. Then what satisfies this condition? The cosecant of theta is less than 0. Remember, the cosecant of theta is going to be the reciprocal of the sine of theta. Okay, so the S stands for the sine of theta, and that's in quadrant 2. So we know that in quadrant 1, everything's positive. In quadrant 2, the sine of theta and the cosecant of theta is going to be positive. And everywhere else, so in quadrant 3 and quadrant 4, the sine of theta and the cosecant of theta will be negative. So this condition is met in quadrants 3 and also quadrant 4. Let's just erase this. And now all you want to do is just say, okay, well, which quadrant satisfies both conditions? Okay, in some cases you might have more than one. In this case, we only have one. It's quadrant 4. Okay, so if you wanted to answer this, you could just erase these. Okay, you don't need them anymore. And you could just write out quadrant 4, or a lot of teachers will just let you write the Roman numeral of the quadrant, just say quadrant 4 like that for your answer. Okay, another type of example you might get is to determine the signs of the trigonometric functions of an angle when, again, it's in standard position and has a given measure. Here it's 110 degrees. So this is really easy to do. This is something where you might want to make a little sketch. So if this guy's in standard position, again, this is going to be your initial side. Here's your terminal side. We know that if it was touching, your terminal side was touching the y-axis like this, it would be a right angle, it would be 90 degrees. If it goes a little further than that, but not far enough to where it's touching here, right? If it was touching the x-axis, you'd have a 180 degree angle or a straight angle. So it's in between those two. So we know it would be in quadrant 2, right? This would be your 110 degree angle there. So in quadrant 2, again, all students take calculus. Very easy. The S tells me that it's sine of theta and also the cosecant of theta. So you can say the sine of theta and the cosecant of theta, those guys are going to be positive, okay? And then the other guys are going to be negative. So you might want to write all these out, or you could say all others are negative. Depending on your teacher and what they ask for, let's just go ahead and write them out. We'll say the cosine of theta. We'll say the secant of theta, okay? Those guys are negative. And then we have our tangent of theta and our cotangent of theta. Those guys are negative as well. So only sine of theta and cosecant of theta are positive for this example. All right, another one of these, we have a negative 150 degree angle. Remember, when you have a negative angle and this guy's in standard position, you're rotating clockwise now instead of counterclockwise. So this is negative 150 degrees. Again, you're starting here and you're rotating clockwise. So again, if you rotated this way, okay, and you got to right here, if it's a negative angle, that would be negative 90 degrees. If it's positive, it would be positive 270 degrees. But here it's negative. So this would be negative 90 degrees. This would be negative 180 degrees. So we're between those two. Again, we're going to land in quadrant 3 here. So that's your negative 150 degree angle. So in quadrant 3, again, just do all students take calculus. So in quadrant 3, you have a T for the tangent of theta, and then also the cotangent of theta. Those are going to be positive. Everything else will be negative. So you have your tangent of theta, and also your cotangent of theta. Those guys are positive, and then the rest are negative. So sine of theta and the cosecant of theta, those guys are negative. And then also your cosine of theta and also your secant of theta, okay, those guys are going to be negative as well. So for this example, the only two that are positive are the tangent of theta and the cotangent of theta. All right, to wrap up the lesson, let's look at a very common type of problem. This is where you're given one trigonometric function value, and you're either given the quadrant or you have to figure out what it is based on the information you have. And basically, you want to come up with all 6 trigonometric function values. So here we're told that the secant of theta is 19 over 11, and the sine of theta is less than 0. Okay, so you can start this off in a few different ways, and there's also multiple ways to do it. But based on what we know so far, we know that the secant of theta, is going to be equal to my r value over my x value. Okay, so if this is 19 over 11, then I know that my r value is 19, and I know that my x value is 11. Okay, so that's important. So I know I'm going to need y, and how do I find y? Remember that r, by definition, is the square root of x squared plus y squared. So let's work on this really quickly. Okay, we'll come back up to this in a moment. So let's just paste this in here so we have a lot of room to work. We know that x is 11. 11 squared would be 121. And I know that r is 19. So I can replace this and say that I have 19 is equal to the square root of 121 plus y squared. If I want to get y by itself, I first have to clear this radical. To do that, I'm going to square both sides. Squaring 19 gives me 361. Squaring this side tells me that this would cancel with this, and I'm left with the radicand, which I'm just going to change the order and say this is y squared plus 121. And now to isolate y, because I'm trying to solve for y, okay? So to isolate this, I'm just going to subtract 121 away from each side of the equation. This would be 240 over here. Over here, this is gone. I'm just going to have y squared. So let me erase all of this, and I'm going to also flip the order around and put y squared on the left and 240 on the right. Again, that doesn't matter. That's just a personal preference. What I'm going to do, let me just kind of scooch this down a little bit. I'll just write this over here because we need some room. I'm going to take the square root of this side, and I'm going to go plus or minus the square root of this side. So 240, if you take the square root of that, you can simplify, right? Because 240 is 16 times 15. So I could say this is 16 times 15. Square root of 16 is 4. Okay, so I could just pull that out and say this is 4 times the square root of 15. Okay, but you do have this plus or minus out in front that is a bit problematic here. So we need one y value. It can't be positive 4 times the square root of 15 and then also negative 4 times the square root of 15. You need one or the other. Okay, so let's go back up and let's go ahead and write all the information that we know. So x is equal to 11. We know that r is equal to 19. And right now we know that y is equal to plus or minus 4 times the square root of 15. But we need to get that down to one single value. Okay, and we're going to do that with the use of this guy right here. Okay, so we're told that the sine of theta is less than 0. So where is the sine of theta less than 0? Remember, if you use your all students take calculus. Once again, this is quadrant 1, 2, 3, and 4. Okay, the S is for the sine of theta, and the A is for all. Okay, so in quadrants 1 and 2, the sine of theta is positive. In quadrants 3 and 4, it's negative. Okay, so let's write 3 and 4 here. 3 and 4 here. Okay, and let's think about the secant of theta. Remember, the secant of theta and the cosine of theta, those guys are reciprocals. Okay, the cosine of theta is going to be positive because this guy is positive in quadrants 1 and 4. So quadrants 1 and 4. So again, when you get this, you're looking for what is the quadrant that matches both. Okay, the quadrant that matches both is going to be quadrant 4. All right, so if we know that this guy's in quadrant 4, then what are the y values in quadrant 4? We know, if we go all the way back up here, that in quadrant 4, your y values are negative. Okay, they are negative. You are below the x-axis. So that tells me, because the y values are negative, that I don't want the positive, I want the negative 4 times the square root of 15. Okay, so once you've figured that out, the rest of it is just plugging things in. Okay, knowing your ratios, having those ready, and then plugging in. As we progress, we're going to go through one more lesson, and we'll go through a section where we start talking about the SOHCAHTOA. Okay, and we'll remember this a little bit easier. For right now, we're putting in terms of x, r, and y. Okay, so we have our sine of theta. Let's just start with that. That is the y value over the r value. Then my cosecant of theta, okay, it's the reciprocal of this. So this is the r over the y, okay? And then let me write out the rest. So we have our tangent of theta, This is going to be our y value over our x value. And then our cotangent of theta is going to be the reciprocal of this. So it's x over y. And then our secant of theta, okay, is given to us, but it's r over x, okay, r over x. But in this case, we already know what it is. It's 19 over 11, okay. Then our cosine of theta, okay, is x over r, but again, it's the reciprocal of this guy, so we can just flip this and say it's 11 over 19. Okay, so let's plug some things in, and let's kind of get some room going here. And let's see, so y, and it's a little bit off the screen here, but we'll just go back and forth. So y is negative 4 times the square root of 15. And r, I know you can't see it, but let's scroll back up. It's 19. Okay, so r is 19. So let me just fill that in everywhere. That way we don't have to keep going back and forth. Okay, so those are the only two places we need the 19. Okay, then y, let me fill that in everywhere. So this is negative 4 times the square root of 15. And let me fill that in here. Negative 4 times the square root of 15. And also here, so negative 4 times the square root of 15. And x, let's just scroll up real quick, that's going to be 11. Okay, so we're done with that. So let's go back up here, put 11, and then go up here and put 11. For the cosecant of theta and the cotangent of theta, you need to rationalize the denominator. So for the cosecant of theta, let's just do this down here. I'll make the whole thing negative. I'll say that I have 19 over 4 times the square root of 15. I'll multiply by the square root of 15 over the square root of 15. Square root of 15 times square root of 15 is, of course, 15. Okay, 15 times 4 is 60. Okay, so you really can't do anything further to simplify. So let's just erase this. Scooch this down a little bit so I have more room. I'll put the negative of, you have 19 times the square root of 15 over 60. All right, so that one's done. And now I just need to rationalize this denominator. So I've got 11 over, let's put the negative out in front. We have 4 times square root of 15. So we'll multiply by the square root of 15 over the square root of 15 again. So we have square root of 15 times square root of 15, which is 15. 15 times 4 is 60. So let's erase all this. Put equals. I'll make the whole thing negative. My denominator will be 60. My numerator will just be 11 times the square root of 15. So 11 times the square root of 15, and I'm all done. In this lesson, we want to talk about the Pythagorean and quotient identities. We'll look at the ranges of trigonometric function values, and also we'll see some examples where we're finding missing function values. So before we jump into the lesson, for reference sake, let's go through the 6 trigonometric functions again. I want you guys to remember the way we've defined this. We've said that r is equal to the square root of x squared plus y squared. Okay, so remember that. So I can also say, if I square both sides, that r squared is equal to x squared plus y squared. So we'll be using this in a moment. So I want you to recall that we defined sine of theta as y over r. We defined cosecant of theta as r over y, where y is not allowed to be 0. Now, you'll notice that, again, sine of theta and cosecant of theta, those guys are reciprocals. Remember your reciprocal identities that we talked about in the last lesson. Then we have our cosine of theta, which is x over r. Our secant of theta, which is r over x. X is not 0. Again, these two guys are reciprocals. Then you have your tangent of theta, which is y over x. X is not equal to 0. And your cotangent of theta, which is x over y. Y is not equal to 0. Again, these guys are reciprocals. Now, our first topic of today's lesson is going to be the Pythagorean identities. So you'll usually see these in your book in this exact manner. So sine squared theta plus cosine squared theta equals 1. Your tangent squared theta plus 1 is equal to your secant squared theta. And then 1 plus cotangent squared theta is equal to cosecant squared theta. So how do we get the first one? So we have our sine squared theta plus our cosine squared theta is equal to 1. We'll see other ways to do this when we get to the unit circle. For right now, we're just going to divide everything by r squared, okay, by r squared. And we know that r squared divided by r squared would be 1. So when we look at this guy, we can say this is now going to be x squared over r squared plus y squared over r squared is equal to 1. Okay, so now using the rules of exponents, remember, I have a 2 here and a 2 here as an exponent, and a 2 here and a 2 here as an exponent, so I can pull that outside of a set of parentheses, right, using my power rules. So I can say this is x over r, okay, this amount here would be squared, then plus you have y over r, this guy here would be squared, this equals 1. Well, by definition, we just saw that x over r is cosine of theta, okay, and then y over r is sine of theta. If we go back up, again, sine of theta is y over r, cosine of theta is x over r. So I could replace this guy right here by saying it's cosine of theta being squared. And I could replace this guy, let me just kind of move this down. I could say this is sine of theta being squared, and this equals 1, okay? So I could apply my exponents and use the commutative property to get into this form here. I can write this as cosine squared theta, okay? And I could write this as sine squared theta, okay? And then I could just switch the order because, again, this is just addition. So when you add two things together, the order doesn't matter. So that's how we get to this form right here. So let's look at the other ones. So we have tangent squared theta plus 1 is equal to secant squared theta. So to get this, let me just erase everything. You're just going to divide everything by x squared now. Okay, quite easy. So divide this by x squared, this by x squared, this by x squared. And we know that this guy is going to be 1. All right, so we know we would have 1 plus, you'd have your y, and I'm just going to write this as y over x, this guy squared, because we know we do that step anyway, is equal to r over x, this guy squared. What is y over x? We know that this is the tangent of theta. So we go back up, again, y over x is the tangent of theta. So you can replace that. You can say this is 1 plus the tangent of theta, this guy squared, is equal to, what is r over x? Well, r over x is the secant of theta. Okay, so we go back and we say this is the secant of theta. Let me make that a little bit better. The secant of theta, this guy's being squared. And again, you can apply your exponents and just say this is the tangent squared theta, okay? And this is the secant squared theta, okay? And then the way we had it was tangent squared theta plus 1 is equal to secant squared theta. So all we'd have to do is just rearrange this and say, okay, I have the tangent squared theta plus 1 equals secant squared theta. Let's look at the last one, which is this guy right here. So 1 plus cotangent squared theta equals cosecant squared theta. And to get this one, I'm just going to divide everything by y squared. And again, it's going to be the same trick overall. So now this guy's going to be 1. So I would write this as x over y. This guy would be squared. Plus this would be 1. This equals, you'd have r over y. This guy is squared. Okay. So x over y, we know that's cotangent, right? So cotangent of theta. X over y is the cotangent of theta. So let's go ahead and say we have cotangent of theta. And I'm just going to put cotangent squared of theta. We know it would end up being that anyway. So then plus 1 equals, what's r over y? So r over y is cosecant of theta, okay? So I'm going to say this is cosecant squared of theta, okay? And again, if I go back, all I have to do is switch the order of these two. So I'll just write this as 1 plus cotangent squared theta is equal to cosecant squared theta. Okay, so that's where those three guys come from. Not very difficult to derive overall, but something you might see in your book and get a bit confused about. All right, so now let's move on and look at the quotient identities. These are a lot easier to understand. You have sine of theta over cosine of theta gives you the tangent of theta. Remember, sine of theta is y over r, and cosine of theta, if I divide it by that, it's x over r. Well, what do we do here? This is y over r times the reciprocal of this, which is r over x, okay? So the r's cancel and you get y over x, which by definition is the tangent of theta. So the other one is the cosine of theta over the sine of theta gives you the cotangent of theta. Well, before you even do this, remember, the tangent of theta, okay, which is y over x, and the cotangent of theta, which is x over y, those guys are reciprocals. Well, look at what I did here. I just took the reciprocal of just what I was working with. I had sine of theta over cosine of theta. Now I've flipped that. I have cosine of theta over sine of theta. So, of course, I'm going to get the reciprocal of what I got before, which is the cotangent of theta, okay? So now all I would have is x over r divided by y over r. This is x over r times the reciprocal of this, which is r over y, okay? So these cancel and you get x over y, which again is the cotangent of theta. All right, so one last thing before we start doing these problems. In a lot of cases, you need to know the ranges of the 6 trigonometric functions because you'll go to solve a problem and you might get something that's not possible, but you think that it is possible, and we'll see that on the first example. I'll show you exactly what I mean. So when you look at your trig functions, you have this range. When you think about sine of theta and cosine of theta, the value needs to be from -1 to 1, including -1 and 1, but in that range, okay? When you work with tangent of theta and cotangent of theta, it can be any real number, okay? It can be any real number. When you work with the secant of theta or the cosecant of theta, well then you could really say this is just that the absolute value has to be 1 or larger, right? Because you can have from negative infinity up to and including -1, and then also from 1 out to positive infinity, okay? So basically the absolute value needs to be 1 or larger, okay? It can't be less than that. All right, so let's look at our first example here. We're going to use the identities to find cosine of theta and sine of theta, given the fact that the tangent of theta is 7/3 and the sine of theta is less than 0, meaning it's negative. So first and foremost, think about the quadrant you're going to be in. Remember that all students take calculus. So we have our 4 quadrants, 1, 2, 3, I'll put 4 marks there, should be 3. So 3 and then 4, okay? So all students take calculus. All right. We know that T stands for the tangent of theta and also the cotangent of theta, the reciprocal. So it's positive in quadrants 3 and also in quadrant 1 because everything's positive in quadrant 1. Sine of theta is negative, okay, in quadrants 3 and 4 because the S stands for the sine of theta. So we know that we're in quadrant 3 because it meets both criteria, right? It's going to be positive for the tangent of theta and negative for the sine of theta. So we will be in quadrant 3, okay? So keep that in mind when you get stuff to know whether it's positive or negative. Now, the other thing is, and this is a very common mistake, remember we just said that the tangent of theta is equal to the sine of theta over the cosine of theta. So what students do is they say, okay, well, sine is negative, and I know that tangent is positive, so what they'll do is say, okay, well, this is going to be -7 over -3, okay, over -3, and they think they're done with the problem. This is a very common mistake. Why doesn't it work out this way? Remember, the range for sine of theta and cosine of theta is from -1 to 1, including those two numbers. So this is not possible. You can't have a -7 and you can't have a -3. So throw that out, okay? So what we're going to do is we're going to take our Pythagorean identity that includes the tangent of theta, and we're just going to plug into that. So we have the tangent squared of theta, okay, plus 1 equals the secant squared of theta. Okay, so you might be saying, why would we plug into that? We're trying to find cosine of theta and sine of theta. Well, remember, the secant of theta is the reciprocal of the cosine of theta, okay? So if we find the secant of theta, we can flip it, we'll have cosine of theta, okay? And once we've done that, we know that our other identity involves sine of theta and cosine of theta. We can plug into that and figure out our sine of theta. So let's just go ahead and knock this out. We're given that the tangent of theta is 7/3. So you would want to plug in here, okay? But remember, this guy is being squared. So when you plug in here, make sure that you square this guy. It's very important, okay? So we come down here. Once you've plugged in, the rest of this is really, really easy. You're just doing some basic algebra. 7 squared is 49. 3 squared is 9. Then you're going to add 1 to that. So get a common denominator. Let's just say this is 9 over 9, okay? This is equal to secant squared of theta, okay? So let's go down a little bit more. I'm going to flip this around and put this guy on the left. So secant squared of theta is equal to 49 plus 9 is going to give me 58, and this is over 9. Now to get this in the form of secant of theta, okay, what I want to do, since this is being squared, I want to take the square root of each side. Remember, on this side, I want to go plus or minus, okay, the square root of 58 over 9. I'm only going to need one of these. Remember, I'm in quadrant 3. That's what we did that to begin with. I'm in quadrant 3. In quadrant 3, the secant of theta is going to be negative, so throw out the positive one. You just need the negative, okay? That's all you want. So let's scroll down a little bit, and we'll say the secant of theta, okay, is going to be equal to the negative of, this would simplify because the square root of 9 is 3, so I'll say the square root of 58 over 3, okay? So we're not looking for the secant of theta. Of course, we want the cosine of theta. And I know this is a bit tedious, but the cosine of theta is found by flipping this guy. So this is equal to the negative of 3 over the square root of 58. Now, when you have an answer with the square root in the denominator, you typically want to rationalize the denominator. So let's multiply this by the square root of 58 over the square root of 58. And that would give me an answer of the negative of 3 times the square root of 58 over 58. Okay, so that's my cosine of theta. I also wanted to find sine of theta. Okay, so sine of theta, what is that equal to? Remember, sine squared theta plus cosine squared theta is equal to 1. Well, I can plug in for the cosine squared theta. I'm just going to plug in the non-rationalized version here. So I'm going to put negative 3 over square root of 58. Okay, you don't need the rationalized one because this is not the final answer. Let's copy this because we're going to run out of room. Go to a fresh sheet here. And let me erase this. We don't need that. And scroll down a little bit more. So if I square this, let's just go ahead and put sine squared theta plus. If I square this, I'm going to get positive, of course, 9 over 58. And this equals 1. Okay, so all I got to do is subtract this away from each side of the equation. So I'll have sine squared theta is equal to 1 minus 9 over 58. And of course, we just get a common denominator going. So I'm going to say this is 58 over 58. And 58 minus 9 would be 49. So this is 49 over 58. So this is 49 over 58. Okay, so to get sine of theta, remember you're taking the square root of each side. So do you want the positive or the negative square root? Remember, sine of theta is going to be negative in quadrants 3 and 4. We're in quadrant 3, so it's going to be negative. So I want the negative square root of 49 over 58. Okay, let me make that reach all the way. And of course, this is equal to the negative of, you have the square root of 49 is 7, so we'd have 7 up here, over, you'd have the square root of 58. And to make this a little bit cleaner, because again, we want to rationalize the denominator, sine of theta is going to be equal to, you have the negative of 7 times the square root of 58 over 58, right? Because I'm going to multiply this by the square root of 58 over the square root of 58, and I'll be done. So sine of theta is equal to negative of 7 times the square root of 58 over 58. All right, so let's take a look at another example. We want to find sine of theta and tangent of theta, given the fact that the secant of theta is -2 and the cotangent of theta is greater than 0, or you could say positive. So the first thing is, what quadrant are we going to be in? Well, where's the secant of theta negative? It's going to be negative in quadrants 2 and also 3. Okay, and then where is cotangent of theta? Where is that positive? It's positive in quadrants 1 and 3. Okay, so 3 matches both conditions there. So we'll say this is in quadrant 3. Okay, so this is going to be in quadrant 3. So when we look at this, we know that our sine of theta will be negative and our tangent of theta will be positive. Okay, so keep that in mind when you're solving this problem. So the first thing is we're given the secant of theta, it's -2. So let's plug in to this guy. We have the tangent squared theta plus 1 is equal to the secant squared theta. So I'm just going to plug in for this. Remember, it's squared, so it would be -2 squared, -2, both the negative and the 2 being squared. If I did that, that would be +4. So let's just erase this and put 4 in here, okay? I'm going to subtract 1 away from each side of the equation, so this is gone, and this would be a 3. So what you have here is tangent squared theta is equal to 3. If I want to find out what tangent of theta is, I'm going to take the square root of each side. Remember, we already said this guy is going to be positive, so I don't need the plus or minus. I just want the principal square root here. So it's just the principal square root of 3. Okay, so that's my tangent of theta. So now that we know what the tangent of theta is, how can we find the sine of theta? Well, one thing we can do, we can flip this guy. Since the tangent of theta and the cotangent of theta, those guys are reciprocals, I can say my cotangent of theta is just flipping this guy. Remember, if it's not displayed as a fraction, just write it over 1 and then flip it. So you can say this is 1 over the square root of 3. We're not going to rationalize this here because this is not going to be our final answer. So what I'm going to do now is I'm going to plug this in. I'm going to plug this in for our Pythagorean identity where it says 1 plus our cotangent squared theta is equal to cosecant squared theta. Remember, the cosecant of theta and the sine of theta, those guys are reciprocals. So I can plug in here, find out what this is, flip it, okay, and I'll have sine of theta. So let's go through and plug in. We'll have 1 plus, I'm going to plug this guy in here, 1 over square root of 3. And this guy's going to be squared, and this equals my cosecant squared theta, okay? Let's get some room going. And so now if I square this, I'm going to get what? I'm going to get 1 squared is 1. Square root of 3 squared is 3. So this is just 1/3. This is just 1/3. To add this to 1, I'm going to get a common denominator and say this is 3 over 3. So this is basically going to give me 4/3. So 4/3 is equal to, and let me write this in another way. So cosecant squared theta is equal to 4/3. Okay, so to solve for this guy, remember the cosecant in quadrant 3 is going to be negative. So I'm going to take the square root of this side. I'll say the cosecant of theta is equal to, over here I want the negative square root of 4/3. So the cosecant of theta is going to be the negative of, the square root of 4 is 2, and then over the square root of 3. So now let's cut this. We'll go to a fresh sheet, and we'll just paste this in right here. So remember, if I want the sine of theta, I just flip this guy. Okay, so if I flip this guy, I'm going to have the negative of the square root of 3 over 2, and that's my answer. All right, let's look at one that involves the quotient identities. So we have find sine of theta and tangent of theta, given the fact that our cosine of theta is equal to -2 times the square root of 2 over 3, and sine of theta is negative. So cosine of theta is negative here. Where is cosine of theta negative? Well, it's negative in quadrants 2 and 3. Where is sine of theta negative? It's negative in quadrants 3 and 4. So again, we have a situation where we're in quadrant 3. Okay, and it doesn't always work out this way. We had 3 problems today where they're all in quadrant 3, but it's going to vary based on the problem you're given. So we know we're in quadrant 3. From here, we're going to say that we know our sine would be negative, it's given to us, and we know our tangent is going to be positive because we're in quadrant 3. Okay, so how do we find our sine of theta? Well, we can use our Pythagorean identity, the one that says cosine squared theta plus sine squared theta equals 1. And I know this is normally reversed, but I'm writing it this way to give myself some room because I want to plug in here. So I'm going to plug in for cosine theta, okay? So I'm going to say this is negative 2 times the square root of 2 over 3. Remember, this guy is squared. It's so important that you don't forget to square things, okay? So if I square this guy, the negative becomes positive, so you can forget about that. 2 squared is 4. The square root of 2 squared is 2, okay? 4 times 2 would give me 8. And then down there you have 3, which is squared, which is 9. So I have 8/9 plus sine squared theta equals 1. Okay, let me erase this. We're just going to kind of stick around here because I'm going to need some of that information, so I'm going to be going back up. So let me just kind of drag this up a little bit so that we stay right here. Okay, so what I'm going to do now is I'm going to subtract 8/9 away from each side. So I'm just going to erase it from over here. I'm going to write this as 9/9. So I have a common denominator, and then we're going to subtract away that 8/9, okay? 9/9 minus 8/9 is 1/9. Okay, so 1/9. Remember, sine of theta is negative. So if I take the square root over here, I want sine of theta is equal to the negative square root of 1/9. Now, the square root of 1/9 is the square root of 1, which is 1, over the square root of 9, which is 3. So it's 1/3. All right, so this is negative 1/3. Negative 1/3. All right, so let me erase this real quick. I'm just going to drag this over here. And I want to find tangent of theta now, given the fact that I know what cosine of theta is and I know what sine of theta is. Remember, the tangent of theta is defined as the sine of theta divided by the cosine of theta, okay? So what I can do, it's going to be hard to fit this in this limited room I have, but I would have that the tangent of theta, let me just write that over here. So the tangent of theta is equal to, the sine of theta is negative, the negative of 1/3 divided by the cosine of theta, which is the negative of 2 times square root of 2 over 3. So let me just copy this, and we're going to go to another sheet. We'll paste this in here real quick. So this is equal to what? It's equal to the negative of 1/3 times, flip this guy, the negative of 3 over 2 times square root of 2. Of course, the negatives are going to cancel. Forget about those. The 3's are going to cancel. So what I'm left with here is 1 over 2 times square root of 2. Let's rationalize. We're going to multiply by square root of 2 over square root of 2. And this gives us the square root of 2 over, square root of 2 times square root of 2 is 2, 2 times 2 is 4. So square root of 2 over 4 would be your tangent of theta.